Hey, Calc BC, here we go. This is going to be lesson 7.4, Taylor series, part 1. It's the first of 2 lessons devoted fully to Taylor series. If you look at Unit 10 of College Board's breakdown of our course, as with this whole unit, we're in the second half of the lessons here, and we're specifically looking actually at lesson 14, finding Taylor or Maclaurin series for a function. We're going to be jumping around through these 5 lessons a little bit. There's a lot jam-packed in here. So this is going to take us 9 lessons to cover this whole unit. So we've got a lot more to go through here. But today we're going to be talking about Taylor series, which is an extension of Taylor polynomials. And you can see that here in this essential knowledge. A Taylor polynomial for f of x is a partial sum of the Taylor series for f of x. We're going to get into some more of this essential knowledge a little bit later, but I wanted to visualize this for you with Desmos. So we're going to start with this. So we looked at this a couple days ago when we started Taylor polynomials. I said, why don't we look at y equals cosine x? And instead of just having, a tangent line, what if we tried to make a tangent curve or a curve that modeled pretty close to this point right here? And we said that the more derivatives of this point on the cosine graph that we take into account, then the better our tangent curve is going to be. So we started with just a tangent line. We then extended to having x squared over 2. And there was no x term because the first derivative right here is 0. So then the second derivative took us to here. And we could just keep going, right? So we did go one step further in that previous lesson where we looked at this, and we could keep going. So here is when we include an x to the 6th. Here is when we include an x to the 8th. And my hope is that you see that the more derivatives or terms that we include, the closer our approximation is to an actual cosine curve, and it actually gets pretty close, even further away from our initial point. So clearly there's a pattern over here, and this doesn't always occur like this, but for a graph like cosine of x, it does work nicely. We have this awesome pattern that develops where we double, or we add 2 to the exponent, and we add 2 to the factorial, and we switch the sign. So I've created a summation down here at the bottom that represents this. So the -1 to the n is switching the sign for every term. The x to the 2n is taking whatever term we're on and doubling the n if we start at 0. So that means this is term when n equals 1. So 1 times 2 is going to be 2, 2 times 2 is going to be 4, 3 times 2 is going to be 6, etc. And on the bottom, we have 2n factorial, which follows the same pattern. And so what I'm going to be able to do here is show you, without actually typing all of the terms out, what happens when I change the upper bound of this summation. So right now, it's only doing terms for when n equals 0 and n equals 1. So that's representing 1 minus x squared over 2 factorial, because that's the first 2 terms. So I can change the upper bound, and really quickly, the graph is going to show us what happens when we include more and more terms. So there's the third, there's the fourth. I think that's as far as we got with the earlier examples. Yeah. So I can just keep going, and you can see that every time that I increase the number of terms, our approximation gets better and better, further and further away from where we're centered at x equals 0, which is pretty dang crazy that all of that stuff on the sides gets closer to the curve, all because we're dealing with the several derivatives down from this point right here. It makes the rest of the curve kind of model after what cosine really looks like. And so I want you to think about what's going to happen if, let's say I change this number right now to 100. I'll do it. So I've changed it to 100, and it's getting really good at looking like cosine. In fact, I think it's just now updated. You can see for everything we can see from -10 to 10 along the x-axis, it looks exactly like cosine. So imagine that I could put infinity in here and make this a true series, a true infinite series. Then our series would be a perfect representation, not just an approximation, but it would be a infinite polynomial that represents the same exact function as cosine of x. And for some reasons, which we'll get into later in this unit, having an approximation that can be represented as polynomials instead of a trig function can be really helpful for certain things. So that is the preview here of what we're looking at. We're just kind of extending our idea of a Taylor polynomial to a Taylor series. And yeah, we're going to switch over to the notes. So here we go. All right, 7.4, Taylor series part 1. A few days ago, we learned to find a Taylor polynomial for a function f. Today, we will extend our knowledge of Taylor polynomials to find a Taylor series for a function f. The Taylor series centered at x equals c is given by this. This should all look familiar. We are going to be literally plugging or like leaving n in for this right here, and this is going to be called our general term. With the dot, dot, dot showing that it goes on forever. And you can also write it in summation notation. And just like before, if c equals 0, this series is called a Maclaurin series. So let's just jump right into an example. Let's find a Taylor series for f of x equals e to the 5x centered at c equals 2. Give the first 4 non-zero terms and the general term. So we're going to start this just like we would with the Taylor polynomial. We need the first 4 non-zero terms. So I am going to write out that f of x equals e to the 5x. And we're going to need at least the first 3 derivatives in order to get 4 terms, right? Because this will count as one of our first terms, well, as our first term. And then I'll do f prime, f double prime, f triple prime. So let's think about what's happening here. E to the 5x, when we take the first derivative, we're going to have to multiply that by 5. For the second derivative, we're going to have to multiply by 5 again. For the third derivative, we're going to have to multiply by 5 again. And then let's actually plug in 2 here because we're centered at 2. So we need f of 2, prime of 2, etc. And all that's going to happen is the exponent's going to become 10, right? Because we're going to have to do 5 times 2. Everything else stays the same. So we have e to the 10, 5e to the 10, 25e to the 10, 125e to the 10. And so if we were just going to write out the first 4 non-zero terms, following along with the formula up here, which is basically the same as a Taylor polynomial, we would have e to the 10 plus 5e to the 10 times x minus 2 plus, where are we at here, 25e to the 10 over 2 factorial times x minus 2 squared plus 125e to the 10 over 3 factorial times x minus 2 cubed. And then what we do, so we wrote the first 4 non-zero terms. Then we're going to give the general term. So just like in the formula, I'm going to write plus dot 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 plus, and then I'm going to try to write the general term here. And instead of just writing f to the n factor, f the nth derivative of f at c, we're going to try to find a pattern in our derivatives. And you should be able to tell we're multiplying by 5 every time. So if we wanted to write out like the general pattern of the derivative for some nth derivative, let's take a look. So for the first derivative, we multiplied by 5 once. For the second derivative, we have multiplied by 5 twice. For the third derivative, we have multiplied by 5 3 times. So couldn't we just write this as 5 to the n? And each one's multiplied by e to the 5x. So that part doesn't need an n. And that's going to be kind of how we generally phrase this. If I could just write the general term specifically for x equals 2, it's going to be 5 to the n times e to the 10. So what that means is to write out this general term, I'm going to write in the numerator 5 to the n e to the 10 over n factorial times x minus 2 to the n. So that is just a general way of writing. So we could take any n and plug it in here and get an answer. So I'm going to just continue to write just like we have up here, plus dot, dot, dot to show that this goes on infinitely. And now we have the first 4 non-zero terms and the general term, which crazily is going to exactly represent, not approximate, f of x equals e to the 5x. All right. There are 3 special Maclaurin series that you must know, specifically for the AP exam and for a quiz in our class. You should know e to the x, sine of x, cosine of x. We are going to add 1/4 series to this list, but for today, we need to know 3 of them: e to the x, sine of x, and cosine of x. You should know these patterns going in to a quiz or to the AP exam without having to derive them like we're going to do just now. So we're going to derive them once now, but then you're just going to have to know these patterns, which, the patterns are pretty clear, so it shouldn't be too bad. You just have to kind of memorize a little bit, but we'll get to that. So let's just try to derive e to the x. So just like we did up top, we're just going to find the general Maclaurin series for e to the x. So for e to the x, if we just wanted to kind of think about it, the initial function is e to the x, and the first derivative of e to the x is e to the x, and the second derivative of e to the x is e to the x, and so on. And since we're looking at Maclaurin, that means that we're centered at 0. So we're going to be plugging in 0. So f of 0 is e to the 0, which is 1. That means f prime of 0 is also going to equal 1. And f double prime of 0 is also going to equal 1. And all of the derivatives from then on are going to equal 1. So if we wanted to write out this pattern, as seen at the top of the page, the first term will just be 1. The second term will be x. The third term will be x squared over 2 factorial, then x cubed over 3 factorial. And you can tell because if we look back up at the formula, all of these f of c's, f prime of c's, f double prime of c's, they're all equaling 1. So they're just going away and leaving everything else. And so we just end up with this nice looking pattern, which becomes x to the n over n factorial over time. And you can see here we're plugging in 0 for n first, and then 1 for n, and then 2 for n, and then 3 for n, etc. And so yeah, so this works for n greater than or equal to 0. So n is going from 0 to infinity. Okay, great, let's keep going. For the next one, to derive a series for sine of x, we're going to try to follow the same pattern. So we're going to start with finding all the derivatives. So we've got sine, cosine, negative cosine, back to sine. It all started over. And then we're centered at 0. So f of 0 is going to be the sine of 0, which is 0. F prime of 0 is going to be 1. And then we end up with what? 0, -1, 0, 1, etc. So that pattern is going to continue. So just thinking about plugging in each of these numbers in this pattern, back into this formula up top. And what's going to happen is a lot, like every other term is going to cancel out, starting with the first one. So we're going to just start with x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus. Okay, so you can see we have all of the odd numbers left over and the signs alternate. And if we wanted to write out the general term, we got to look for the pattern here. We got to figure out how we're going to represent that we're only including odd numbers and alternating signs. We could write it like this. We could write it as -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So let's think about that. If this is n equals 0, we've got -1 to the 0 power, so that goes away and equals 1. We have x to the 1st over 1 factorial, so that just gives us x. When we plug in 1, we're going to get x to the 3rd over 3 factorial, and -1 to the 1st makes this a negative term, and so on and so on. So once again, n is going to be greater than or equal to 0. Okay, cosine, which is the next one we're going to look at here, is actually what we graphed at the beginning of the lesson on Desmos, but we're going to derive it this time. So we have f of x equals cosine x, and then the first derivative is going to be negative sine, and so on. So it's going to become negative cosine, and then sine, and then cosine, and so on. And we're centered at 0 once again, so f of 0 is going to be the cosine of 0, which is 1, and then it's going to go to 0, and then -1, and then 0, and then 1, and so on. And so if we plug all of those in, just like we did on Desmos, it's going to become 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And it keeps going. And then we eventually get to the general term of -1 to the n times x to the 2n over 2n factorial, with n being greater than or equal to 0. And you could try plugging each of these into there and you would see that that works. Okay, so that is what we're looking at. You can see this time we only have the even numbers for our powers and our factorials. All right. So those are 3 of the 3 of the Maclaurin series that you must know, and we'll have lots of practice looking at those. So let's keep going here. We can manipulate these 3 special series, or any series that we are given, to find other series by using techniques called manipulation techniques. These include substituting into the series, multiplying or dividing the series by a constant and or a variable, adding or subtracting 2 series, or differentiating or integrating a series. And we'll see some practice with that starting today. So let's take a look at this first example here. Find a Maclaurin series for f of x equals sine of x squared. Give the first 4 non-zero terms and the general term. So we would start by looking at the Maclaurin series for sine of x. And so we have sine of x, which we just found, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. We're looking for the first 4 non-zero terms. So I'm just going to write those 4 of sine of x. And the general term, which we said was what? This is for sine of x. So it became -1 to the n x to the 2n plus 1 over 2n plus 1 factorial. And now the question is, can we plug in x squared? So just like any function, if we're changing what we're plugging in or substituting in x squared for x, we're going to do the same thing on the right side. So that's what I'm going to do. So let's think about this. We're going to have x becomes x squared. And in this second term here, we have x cubed. So think about that x is becoming x squared. You know what? Since this is the first time we're doing this, I'm going to write it out twice. So we're going to have x squared replacing the x, and then that gets cubed. Everything else just kind of falls into place around this, but every x I'm replacing with an x squared. Including in the general term. And so then I would probably write one more step where I actually kind of multiply the exponents, right? Because x squared cubed is the same as x to the 6th. So let me try to squeeze that in here. So we have x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. You can see this is making a new pattern among the exponents, which is going to automatically become clear as we multiply 2 times the 2n plus 1 in the general term. So we get negative 1 to the n, x to the 4n plus 2, all over 2n plus 1 factorial. Okay, so that's our final answer for that one. Letter B, use your answer to find a Maclaurin series for f prime of x. So now what we can do is, instead of trying to find the derivative of sine of x squared and make use of that, because it's going to be what? Cosine of x squared times 2x. Maybe for reasons, which we'll talk about later, it would be more helpful if we had a polynomial to represent that derivative. So we're going to use the Maclaurin series for f of x to find the Maclaurin series for f prime of x just by taking the derivative of each term. So we are going to have f prime of x equals, and we're just going to take the derivative of each of these. So we'll have 2x minus 6x to the 5th over 3 factorial plus 10x to the 9th over 5 factorial minus 14x to the 13th over 7 factorial. And then the general term, which will become what? We'll have negative 1 to the n times 4n plus 2 times x to the 4n plus 1 all over 2n plus 1 factorial. So we just did the same power rule in the general term. And we don't need to simplify more than that. So there we go, we got it. All right, let's take a look. One more set of examples. Find a Maclaurin series for f of x equals x times cosine x. Give the first 4 non-zero terms and the general term. We can actually multiply a series by a constant or by a variable. So when f of x equals x times cosine x, we can represent that as x times the series for cosine x, because those two things are equal. So we can just replace it. So we said at the top of this page that cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. The general term was negative 1 to the n, x to the 2n over 2n factorial. And all we need to do is just multiply or distribute the x. So we could say our f of x now equals x, and all the exponents on the x's are just going to go up by 1. So we have x cubed over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial. And the general term is going to be x to the 2n plus 1. There we go. Hopefully that makes sense. That's all we needed for that one. And now for letter B, use your answer to A to find a Maclaurin series for the integral of this function from 0 to x. So we've changed the variable to t just because we're going from 0 to x for the integral bounds. But all this is really saying is take the integral of this series. So that's what we're going to do. So we're going to say integral from 0 to x of f of t dt, and we're just going to use our general integration rules. So this first term is going to become x squared over 2. The second term is going to become x to the 4th. We have to divide by the new exponent, and there was already a 2 factorial under there. The next term is going to become x to the 6th over 6 times 4 factorial. The next term is going to become minus x to the 8th over 8 times 6 factorial. And you can see this kind of leads to some very interesting patterns. We've got this pattern of even numbers going on in our denominator. But let's see, what's our general term going to be? So we're going to integrate this. It means we add 1 to the original exponent, x so becomes x to the 2n plus 2. And on the bottom, we're going to have to multiply by the new exponent. So it's going to be multiplied by 2n plus 2 times the original denominator, 2n factorial. Okay. So that's it. All right, so hopefully that makes sense. It looks like a lot, but it's just using our basic derivative and integration rules, our power rules there on some pretty extensive series. So hopefully that makes sense. Let me know if you have any questions. Good luck with the homework and have a great day. Thanks for watching.